Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
I have to be honest, this problem I've never done before. I just thought, I'll do something new on my lecture this time around. So here we go. I just copied and pasted this in, and it could go very bad or very great. So let's see. A Ferris wheel with a radius of 10 meters is rotating at a rate of 1 revolution every 2 minutes. How fast is a rider rising when his seat is 16 meters above ground level? Well, I've read the problem. I kind of understand what's going on. So read it. To understand this, I am definitely going to draw a picture. So the picture goes like this, I'm guessing. I have ground. I have a Ferris wheel. And let's see, I have a radius on that Ferris wheel. I like red for radius, honestly. So the radius of this Ferris wheel is, 10 meters? Okay, 10 meters. Let's see. That picture's pretty much going to do it. It rotates is rotating at a rate of 1 revolution every 2 minutes. This is just to give us a speed for an angle. I can easily see that. So I'm going to state that in a moment. But I do want to label where this rider is. So let's just say this rider got to 16 feet above ground. Now remember, if the radius is 10, that distance is 10. This distance would be 20 altogether. So the rider is somewhere around here probably. I'll call that R for the rider. How's that? Okay, so we want to know how fast is that rider rising when his seat is 16 meters above the ground. So I'm going to just make a little note here that in the end we want that to be 16 meters. I get the idea. So now that we have that done, we'll go ahead and now label the knowns and the unknowns. And basically, it's much easier to label what we want here, I think. So let's take a look. What do we want? How fast is the rider rising when his seat is 16 meters above the ground? Now, because they're giving me the fact this rider is 16 meters above the ground level, I can I can exactly do this. I could start the problem here. So I could just go ahead and say this is H. And I just want to know how quickly that H is moving. We'll add, obviously, we want this full distance to be 16 meters, but that actual distance right there is 10. We're going to stop time when H is 6 more. So H plus 10 should be 16 really, but we want to find how fast is the rider rising. So what is dH dt? What's the rate of change of his height when H is equal to 6? Yes, I understand 16 is what they want, but 10 feet of it or 10 meters of it is concrete down below us. So I'm just saying when that H there is 6 more, how quickly is he rising? I think that's probably the easiest way to do this problem. By the way, this is a radius of 10 there. And what were we given? Was there any rate that we were given here? Yeah, a rate of 1 revolution every 2 minutes. So that means it goes through 2 pi radians every 2 minutes. That's the rate of change of the angle. That's how quickly the angle is changing. So I'm going to call this theta, and it's going through a rate of 2 pi radians every 2 minutes, or in other words, pi. So the rate of change is pi radians per minute. All right, so we need, that's labeling is done. Read, understand, label. Now we need the master equation. Let's see here. Oh, that's going to be pretty nice because it's a right triangle. So if you take a look at this right triangle right here, that involves h and theta. And remember, we want to relate that variable and that variable. Well, that's pretty easy. The sine of theta relates h and 10. So let's go ahead and do that. The sine of theta is equal to h over 10. Perfect. That's our master equation. Doesn't look like much of a master equation, does it? But it totally is the master equation. Then you can go into the rate equation. Let me put a little check mark there and put number 5, rate equation. The rate equation, we just take derivative with respect to time of both sides. The derivative of the sine is cosine of theta, and then times d theta dt by implicit differentiation is equal to 1/10 times the derivative of h with respect to time. All right, perfect. And now, let's see, sub and solve. Now, the sub and solve, I have a feeling, is going to be kind of weird here. So let's find out why. I could easily see why. All right, so the sub and solve. Let me zoom in. Sub. The only thing that we can sub in here really is h equals 6, right? Because that's when we want to know, that's when we want to stop time, is when h is 6, or the total height is 16. So we're going to sub h equals 6. Well, if you look at our rate equation, there's not an h in there to sub in for. However, we have a right triangle. And if we let this h equal 6, you can find out what theta is. Actually, you just use Pythagorean theorem to find out what this missing side down here is, so you can find the cosine of theta. So, oh, by the way, the other thing we can solve is d theta, or sub n is d theta dt. That's pi. We've calculated that earlier. So, using Pythagorean theorem on this right triangle, 100 minus 36 is 64. So that's an 8. Well, 64 and 37. Oh, that's nice. So that's 8. Great. Well, the cosine of theta then, when h is 6, is going to be 8/10, or divided by 2, 4/5. So there we go. That's what we're going to sub in. This will imply cosine of theta is 4/5. And so now our rate equation becomes 4/5 times pi is equal to 1/10 dh dt. Or in other words, multiplying both sides by 10 to 8 pi is dh dt. And so that's 8 pi meters per minute. That's the rate of change of that person's height. So at 16 meters, the person's elevation is changing at a rate of 8 pi meters per minute, about 25 meters per minute, something like that. He's still increasing the height. That's a pretty fun example. I like it. I'd never done that before, but a pretty good example. I like it a lot.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.